Hello, ladies and gentlemen. Today we are going to be looking at the effects of plate tectonics and currents on global climate. And we're really going to take a look at reading. You can also find this reading on page 664. Changing continents, ocean currents, and climate. How ocean currents affect regional climates. Please follow along with my cursor as I go through and read it and talk about it. In the Investigate, you used models and maps to explore the factors that affect the flow of ocean currents in 3 geologic periods. This digging deeper will help you understand more about those factors, and I will be posting a video about that. A community near an ocean has a more moderate climate than one at the same latitude inland. This is because water has a much higher heat capacity than rocks and soil. Oceans warm up and cool down more slowly than the land. Currents are also an important factor in a coastal climate. A community near a cold ocean current has a cooler weather than one near a warm ocean current. For example, Los Angeles is located on the Pacific coast near the cold California current. The city has an average daily high temperature in July of about 75. Charleston, South Carolina, is located at a similar latitude. However, it is on the Atlantic coast near the warm Gulf Stream. See Figure 1, and we'll take a look at that. Charleston's average daily high temperature in July is 90. So down here we have the warm Gulf Stream. We're looking at thermal infrared image, so we're looking at the temperatures. And we have much higher temperatures in red, and we have that hot water moving up the southern coast past Florida, Georgia, South Carolina, North Carolina. And we have colder areas in purples and blues. So we have the cold Labrador current up in the north going down by Labrador, Prince Edward Island, Nova Scotia, and even northern areas of Maine. And you will also find that coastal communities will be warmer during the winter and cooler during the summer because of the ocean, and the ocean will warm up the area during the summer, warm up the area during the winter when it's much colder and that nice above freezing water is warming up the area. So think about any of those negative 10-degree days that we had over the winter and how the ocean is warming up our area. And it might have been colder in Bangor than it was here because of that. And at the same time, Bangor will be much warmer during the summer, and it will be cooler here because the ocean is 50, 60 degrees or so during the summer, and it will be cooling us down. Let's read on. Oh, and heat capacity. So water will be able to it will take water longer to heat up and longer to cool down. And we see this during the summer and during the winter when it takes so long to warm up, takes so long to cool down during the winter. And then sand and land heats up much faster, so this is Bangor, and cools down much faster as well. Anyway, continuing on. How ocean currents affect global climate. Patterns of ocean circulation also have a strong effect on global climate. The equator receives more solar radiation than the poles. However, the equator is not getting warmer, and the poles are not getting colder. That is because oceans and winds transfer heat from low latitudes to high latitudes. One of the main ways that ocean transfers this heat is by the flow of the North Atlantic deep water, abbreviated NADW. It works in the following way. In the North Atlantic, the ocean water is cold and salty. It sinks because of its greater density. It flows south at a deep level in the ocean. Then at low latitudes, it rises up towards the surface as it is forced above the even denser Antarctic bottom water. And we'll take a look at figure 2 in a minute. Water from low latitudes flows north at the ocean surface to replace the sinking water. As it moves north, it loses heat. This slow circulation is like a conveyor belt for transferring heat. This kind of circulation is usually called thermohaline circulation. So thermal, you wear your thermals to keep you warm in the winter. Thermo, heat, stands for temperature. And haline, geologists will call salt halite, and haline stands for saltiness. When this conveyor belt is disturbed, the entire global climate is affected. For example, about 12,000 years ago, Earth was coming out of a glacial age. Glaciers were melting rapidly. The melting glaciers discharge a lot of water. So when they discharge, it's kind of like being discharged from a hospital. It's given off. You're allowed to go. A lot of water into the North Atlantic. So the melting glaciers released a lot of water into the North Atlantic in a short period of time. The fresh water decreased and lowered the salinity of the ocean water. This reduced its density, so it became less dense. This decrease was so great that the production of North Atlantic deep water was decreased. There wasn't a lot of it. This seems to have plunged the world back into a short cold period. This period lasted about 1,000 years. So there wasn't as much of the North Atlantic deep water being produced. So this cold deep water wasn't moving away from the poles. The warmer water wasn't able to move towards the poles. So heat wasn't moving from the equator like it usually does and like it does now. So as a result, another ice age or cold air period in time would have occurred. Let's continue on. How plate tectonics affects global climate. The positions of the continents on Earth change as Earth's lithospheric plates move, so our continental plates and our oceanic plates. Plate tectonics is a theory in which the lithosphere is divided into a number of plates that move relative to each other. We've learned about this. The arrangement of continents has a strong effect on Earth's climate. Think about the requirements for the development of large continental ice sheets. Glaciers form only on land, not on the ocean. For an ice sheet to develop, there has to be a large land area at high latitudes, so up near the poles, where snow can accumulate to form thick masses of ice. Where the oceans occupy polar areas, accumulation of snow is limited. There just isn't as much of it by melting in the salty ocean waters. Polar oceans, such as the Arctic Sea around the North Pole, are mostly covered by pack ice. This ice is no more than several meters thick. Today, there are two continental landmasses with permanent ice sheets. They are Antarctica in the southern hemisphere and Greenland in the northern hemisphere. You'll notice that they don't talk about Canada. The continent Antarctica has not always been centered around the South Pole. About 200 million years ago, all of Earth's continents were welded together. They formed a single continent. This was the supercontinent called Pangaea. Pangaea eventually rifted or broke apart into several large pieces. One of these pieces moved slowly southward. This is the present Antarctica. Eventually, it moved close enough to the South Pole. Ice sheets formed. In recent geologic time, Antarctica has been directly over the South Pole. Therefore, the Antarctic ice sheet has remained in existence even during interglacial periods. Scientists know this because otherwise global sea level would have been much higher during the interglacial periods of the past million years. You modeled the development of the Antarctic Circumpolar Current, ACC. This ocean current flows eastward, clockwise, around Antarctica. It is the most important current in the Southern Ocean. It is also known as the West Wind Drift. The ACC reaches depths between 2,000 and 4,000 meters. and a width of up to 2,000 kilometers. This is much deeper than most of the other surface currents that we've seen. This huge area produces one of the largest ocean currents by volume on Earth. The current is driven by strong winds between 40 degrees south and 60 degrees south. The winds average 15 to 24 knots. The mean or average ACC temperature ranges from -1 to 5 degrees Celsius, so this is right around freezing, depending on the time of year and location. Northerly flows feed cold water into the Atlantic, Indian, and Pacific Oceans. They redistribute heat to influence patterns of temperature and rainfall. The waters of the ACC freeze during the winter and warm during the summer. This strongly affects the renewal of deep ocean water. Many scientists refer to that ACC caused or stabilized infer that the ACC caused or stabilized a full glaciation of the Antarctic region. This would have occurred around 33 to 34 million years ago. The last two barriers to the south flow were south of Tasmania and south of South America. Scientists continue to study marine and tectonic evidence. They do so to try to determine the exact timing of the opening of the deep gap that controls the flow and affects climate. So because the strong winds around Antarctica are able to blow right around Antarctica, it keeps that cold surface water circling right around Antarctica. And it does this, it keeps that cold air in and keeps it there. This makes it colder. This makes our Antarctic bottom water probably a lot colder than it otherwise would be, and probably why it's colder than the North Atlantic deep water. And because our continental plates are far enough away from Antarctica, that circumpolar current that goes right around Antarctica, so circumpolar goes around Antarctica, is able to keep that cold water there and keep it colder. And this has stabilized that Antarctic climate and has made it continue to be so much colder. Okay, last page. Presently, most of Earth's continental land area is in the northern hemisphere. Much of North America and Eurasia is at a high latitude. Ice sheets form during times when decreased global temperatures, or with decreased global temperatures. During times of increased global temperatures, ice sheets melt away. The North American and Eurasian ice sheets have melted away completely during these parts of the cycle. So you don't see many ice sheets or glaciers around in North America or Europe or Asia right now. There are some, but not a lot. It is very different in the southern hemisphere except for Antarctica. There is not a large amount of continental land area at high latitudes, so not many mountains up that high. Therefore, large continental glaciers do not form. So you don't have many continental glaciers down in the southern hemisphere. Plate tectonics affects climate in other ways besides changing the positions of the continents. Volcanoes, we've learned about this, form along active plate boundaries, so your convergent boundaries and your divergent boundaries. Increases in activity at these margins cause increases in volcanic activity. Volcanoes release carbon dioxide. Carbon dioxide is a gas that traps heat in the atmosphere. You will learn more about carbon dioxide in the following section, which is in our next unit. In this way, plate tectonics might cause global climate to warm. However, volcanic eruptions also add dust to the atmosphere. Dust blocks out some solar radiation. This tends to decrease global temperatures. We know about that. Continent-continent collisions create large mountains. They go boom and they go up. The Himalayas and the Alps are modern examples. Many scientists believe that the wearing down of such mountain ranges uses up carbon dioxide from Earth's atmosphere. The chemical reactions that break down the rock use carbon dioxide from the atmosphere. This means that there is less carbon dioxide in the atmosphere. The result is cooler global climate. Collisions between continents produced the supercontinent Pangaea. The result was high mountain ranges, such as the one at the present site of the Appalachian Mountains. The Appalachians were much taller and more rugged when they first formed. They may have been as tall as the Himalayas. See Figure 5. The mountains have undergone 300 million years of erosion. This has given them their lower and well-rounded appearance. On a global scale, all that weathering may have contributed to the period of glaciation. Scientists think that this period began about 300 million years ago and ended about 280 million years ago. Now I'm really curious, if you guys were to go back to Earth Viewer, mind you I haven't done this yet, and go back to Pangaea, see if the amount of carbon dioxide went down in the atmosphere after Pangaea was formed. See if the temperature and the climate goes down. I'm curious. I wonder what you'll find. In your checking up section and in your reading guide, you will find these three questions, and then some other questions to stretch your thinking as well.